Hi, and welcome to AP Chemistry Review. It's me, Dr. V, and it's time to work on some free response questions. Today, we're going to do question number 1 from the 2018 exam. This is one of the long free response questions. It's scored out of 10 points. So we'll go through it part by part by part. There are a lot of parts, and we'll talk about how it was scored and what you need to do. But I'm going to be honest with you folks. This webcast will be most useful to you if you've already sat down to do this question on your own. Alternatively, you could work through each part and then listen to my response. That's how it's going to help you the most. So let's jump right in, okay? You'll need your calculator, you need your periodic table, you'll need your formula sheet, right? This is a fairly long question and you want to be set. So a student performs an experiment to determine the value of the enthalpy change, delta H of reaction, for the oxidation-reduction reaction represented by the balanced equation above. And they give you the full equation. Okay, so the first thing we're asked to do, part A, determine the oxidation number of chlorine in sodium hypochlorite, NaOCl. Okay, so in order to do this, you need to know your oxidation number rules. If you don't remember them, I've got a webcast. You need to know those rules right off the top of your head. So this part was scored out of 1 point. It's pretty much all or nothing. Right, there's really not any wiggle room here. So sodium in a compound will have an oxidation number of +1 because it's a monatomic ion. All right, oxygen in a compound almost always has an oxidation number of -2. Again, rules you should just know. All right, we also know that the sum of the oxidation numbers for a neutral compound is 0. So we want to know chlorine. And so we need to add everything up where chlorine is what we're solving for. So the +1 plus the X for chlorine -2 has to add up to 0. And so we get an oxidation state of +1. And that's our final answer. All right. And that's what you needed to have. Now, you didn't have to write out all your work. If you could just do some scratch work and come to +1 and write that down, you're good to go. But you do want to know where this is coming from so you can answer other questions. All right. Let's go on to part B. All right. Calculate the number of grams of sodium sulfate needed to prepare 100.00 mils of 0.500 molar sodium thiosulfate. Okay, so place to start with this molarity formula. We have a volume, we have a molarity. All right, it was scored out of 2 points. All right, so there is some room to get one of the points and not both of them, but you should be able to get both points. So you should remember that molarity is defined as the moles of solute over the total solution volume in liters. This equation is on your formula sheet, right? And I always encourage my students to rearrange things. So since we need to solve for the solute, the moles of the solute would be the molarity of the solution times the volume in liters. And we substitute and evaluate, and we get a number of moles for our solute. All right, so this is really what got you the first point, was doing this. You then need the molar mass of the solute. Turns out to be 158.10 grams per mole. And my recommendation is when you're solving for molar masses or using molar masses, always keep at least 2 digits after the decimal place. If the periodic table gives you more, use what you're given. All right, so now that we know the moles and we know the molar mass, it's quite easy to calculate the mass of the solute that we need and report that to the correct number of significant figures. So 0.5 moles times 158 grams per mole gives us a mass of 7.91 grams. Now, if you chose to do this with a one-step calculation where you have all the pieces linked together, of course that's fine. We're looking for work that supports your answer and an answer that is consistent with the question that you're working with. But a small mistake in any one of those places might cost you the point. All right, so if you had linked this all together, or if you had substituted the grams per mole into the molarity formula, of course that's fine, because you're implying that, but make sure it's all there for the 2 points. Okay, for part C, all right, it goes on and says, in the experiment, the student uses the solutions shown in the table below. Well, there are 3 reactants. We're given the concentration and volume of all of them. Using the balanced equation for the oxidation-reduction reaction and this information, which reactant is the limiting reactant? Justify your answer. All right, so it is a limiting reagent problem. That's what we're asked to do here. All right, this was 1 point. Either you got it or you didn't. You needed to correctly identify the correct limiting reagent and back it up with math-based reasoning. We're asked to justify our answer. Now, there's more than one way to answer this. Here's what I did. All right, what I noticed is that I've got the same concentration and the same volume for each of the 3 solutions, which means I've got equal moles of each reagent going in. All right, and I can easily calculate that from the molarity formula. All right, so that's it, makes my life just a little bit easier that they're all the same. So the way I teach my students to handle limiting reagent problems is to pick a product and solve for that product using each reactant and the amount that you have. So how many moles of sodium chloride would I get from the Na2S2O3? How many moles of sodium chloride would I get from the NaOCl? How many moles of NaCl would I get from the NaOH? And I'm just really doing a mole-to-mole calculation here, all right? And what I see when I do these is that the amount of NaOCl gave me the smallest quantity of NaCl, which means NaOCl must be my limiting reagent. All right, and so that's what I need to identify the limiting reagent, and I've got enough work to justify it. Now, because they're all equal moles, you might have noticed that the one with the highest coefficient is going to then give me the smallest amount of product. So you can use that reasoning too, but you do need to state how you got there, and you need to really be able to back up that math-based reasoning. Okay, so the solutions, all originally at 20.0 degrees Celsius, are combined in an insulated calorimeter, and the temperature of the reaction mixture is monitored as shown in the graph below. According to the graph, what is the temperature change of the reaction mixture? Okay, so this was a 1 point problem. Again, it was pretty much all or nothing. Either you got the point or you didn't. All right, so delta T is usually calculated as T final minus T initial. And here, that's an easy thing to remember. Sometimes with endothermic reactions, students forget to do that, and then they don't have the right signs. You need to pay attention to those little details. All right, the T final, we're going to read off the graph. I estimated it to be about 32.5 degrees Celsius. We were given the initial temperature of 20.0 degrees. The difference of those is 12.5 degrees. So you should really show the work that you do to support your answer. Just writing down the answer is not always sufficient. All right, but here it's pretty easy. Okay, so now let's go on. The mass of the reaction mixture inside the calorimeter is 15.21 grams. Calculate the magnitude of the heat energy in joules that is released. Assume that the specific heat of the reaction mixture is 3.94 joules per grams per degree Celsius, and the heat absorbed by the calorimeter is negligible. All right, so this actually makes our life pretty easy. They gave us the mass of the mixture. They gave us the specific heat of the mixture. So we really just need to do Q equals MC delta T here. It is a 1 point problem. So again, it was pretty much all or nothing. All right, so we're solving for Q, and we don't need the sign of Q. All right, it would be negative because it's an exothermic process, but that's not our focus here. We really just need the numerical value for Q. All right, we're going to use our delta T from part D, all right, which was 12.5 degrees. And as I mentioned, we were given the mass of the reaction mixture and its specific heat. I'm going to just go off topic for a little bit here. Sometimes when you're doing these MC delta T problems where you're mixing things together, sometimes they've told you the mass of the solute and the mass of the, say, water. If they give you the specific heat of the mixture, they want you to use the mass of the mixture. That's just something to pay attention to with these problems in general. All right, so now it's really just a substitute and evaluate situation. Really very straightforward. All right, so we just plug in the values for M and C and delta T, and I got a value of 749 joules. Great, no problem. All right. Oh, I misspoke earlier. I said it was going to be negative. Well, delta H for the reaction is negative, but Q here that we're calculating is actually for the water. So it is a positive number for the water. That's going to be important when we go on to the next part of the question, because this is E part 1. There's an E part 2, and we're going to need this information for Q to do the next part. All right, so our answers need to be internally self-consistent as we're working, because now we're asked to find the value of the enthalpy change of the reaction in kilojoules per mole of reaction. Include the appropriate algebraic sign. This is where that knowing endothermic and exothermic can come in really handy, because this is an exothermic reaction. The heat was released by the process into the water, and so we're going to end up with a negative value for H. All right, this was scored out of 2 points. All right, and we have to go back and think about our answer to part C as well, where we knew that NaOCl was the limiting reagent. So our other calculations should then depend on that. All right, now this is a place where a lot of students ran into trouble in the 2018 exam. If you look at the balanced equation, the NaOCl has a coefficient of 4. All right, when we're doing things on a mole per reaction situation, we want to have everything compared to substances with a coefficient of 1. Since we've got a coefficient of 4 here, we need to divide by 4 before we go into our delta H calculation. All right, so we're going to take our value for Q that we found in part 1 of this section, divide it by the moles of reaction, and that will get our answer. So Q we had is 749 joules, but if you notice, the problem asks us to do this in kilojoules. All right, so we have to use our answer from the previous part and make sure we get that sign change put in and substitute the values, and we get an answer of negative 1.20 times 10 to the third kilojoules per mole. All right, pay attention to your units, joules versus kilojoules, really easy to miss that. Pay attention to that sign convention. Also paying attention to sig figs. We had 3 sig figs for the joules for Q. We had 3 sig figs for the moles. We want to make sure we report that answer with 3 sig figs. Now, for the free response questions, there's only one part of one question that's actually scored on sig figs, but you don't know what that is going in, so you're better off just always being careful about it. All right, the student repeats the experiment, but now doubles the volume of each reactant. So the same concentrations, but twice as much. All right, why is delta H of reaction the same as what we got in part E? All right, this was also 1 point. So what we have to remember here is that we are reacting twice as many moles of each reactant, okay? Which means Q would be twice as big, right? We're going to, when we go and calculate Q for the amount of water and the total mass, right, delta T, we're going to get a value for Q that's twice as big. But we had twice as many moles going in. So when we do Q over moles, we do actually still get the same answer. And that's really the reasoning that you need to present here, right? So that ratio stays the same and delta H won't change. Okay, last thing we need to do, write the balanced net ionic equation for the given reaction. And for this, you have to really know how to dissociate soluble ionic compounds into their component parts. And I know a lot of my students ran into trouble with this because they didn't always recognize the anions, and I got some goofy responses with that. So the first thing you should do is take all your soluble ionic compounds and write them as dissociated ions. So that's what I've got here. There are 2 sodium ions, the thiosulfate ion, 4 sodium ions, the hypochlorite ion, more sodium ions, hydroxide ions. All right, that's all my reactants. On the product side, I've got a bunch of sodium ions, I've got some sulfate ions, I've got a chloride ion, and I've got the water, which is a molecule and will stay together in its molecular form. It won't dissociate into ions, all right? And the next thing we need to do is cross out any species that are the same on both sides. So that's what I did here. And what's left is your net ionic equation. And truthfully, you can just stop right here. You've crossed them out. You've removed the spectator ions. What's left is your net ionic equation. You do not need to write it again, all right? I did because I did, but in a test setting, that might not make sense in terms of using your time well, right? So it was a question that covered a fair bit of territory in terms of content, had a lot of good skills in it. I just noticed a typo where I've got a couple extra minus signs in there that I apparently didn't take out, but that's okay. It's a good question. These are all skills that AP chemistry students need to be able to do. All right, we will pick up with other questions later. We're going to do a lot of this. So check back in for more AP free response questions. We want to be ready for that exam.